Okay. I think we are live. Yeah. Okay. Welcome everybody to this this session of IAPS at a distance. Today our topic is seismology, and joining us for today we have two speakers, Dr. Daniela Kuhn and Dr. Johann Schweitzer from the International Association of Seismology and Physics of the Earth's Interior. First of all, I want to welcome both of our speakers and thank you for being present for this session for physics students. So today we have a very interesting topic of seismology, which I think is definitely important to sort of expose a bit more physics students to this topic, so they're also aware of it. So first of all, I will just read you the short bios of both of our speakers, and then I will give them the word for their presentations, and then we can have the Q&A. So Dr. Daniela Kuhn is a senior research geophysicist at NORSAR, working in the microseismic group as well as in the seismic hazard group. She earned her PhD in 2005 and worked on various fields within seismology since then. In 2006, she won the Karl Zobritz Award for Outstanding Young Scientists of the German Geophysical Society. She joined NORSAR in 2007 and since 2015 shares her position between NORSAR in Norway and the German Research Center for Geosciences in Germany. Her research interests include induced seismicity, moment tensor inversion, waveform modeling, and fracture mechanics. Welcome, Daniela. And we have also Dr. Johann Schweitzer. He's a principal research geophysicist at NORSAR, Kjeller, Norway, and adjunct associate professor at the University of Oslo in Norway. He received his education from the University of Frankfurt, Germany, and after several postdoc and researcher positions, he moved to Norway in 1997. His principal research topics are seismic arrays, seismic event location, seismic monitoring, structure of the Earth, seismology in polar regions, and the history of seismology. Since 2015, he has been Secretary General and Treasurer of the International Association of Seismology and Physics of the Earth's Interior, which he is representing here today. So now I give you the word for your presentation. Thank you very much.
Thank you very much. How we are doing it? I have now to share the screen, or?
Yes, I believe you have permissions for that already. If you can try.
Okay. Share the screen, and then I go here. And I think I have to press this here. I don't know what you are seeing now.
Your PPT, yes, yeah, now it looks good.
Okay. Good. Thank you very much to be invited to give seismology a chance in the physics world and to represent some of our work and ideas, what we are working on. And I want to start with some old pictures from seismic events in Japan, and the black and white picture in the center in the bottom is from the famous San Francisco earthquake in 1906, and where we see some effects of earthquakes on the Earth's surface. But seismology is not only earthquakes; it's much more. a lot of science about earthquakes itself, but also about wave propagation in the earth, and seismology is, as I see it, a science with many possibilities for interdisciplinary work together with other colleagues. And I will try to give a short overview, and I'm also aware that the one or the other topic one may have lost, but I hope to make the whole thing interesting for you and all of you. So, as I said, seismology is not only earthquakes and destruction, and this is known since now many years. The modern seismology started at the late of the 19th century, when the German physicist and astronomer Ernst von REBEUR-PASCHWITZ was the first one who observed some seismic signals from an earthquake in Japan. With a small pendulum he had installed in Germany, and he recorded signals which had gone through the whole globe and were observed. And this was somehow the kick, and the start for seismology as an international science. He was quickly aware of all the possibilities of what this will be. And he proposed in 1895 in an article in German, I tried to translate it into English, he proposed the establishment of an international net of seismic stations for the systematic observation of seismic waves which traveled along the surface or through the body of the earth. And for this, the goal was to find more out about the structure of the earth. Important for such a success of a network is that all stations are equipped with similar instrumentation and which records the signals with an equal sensitivity. And of course, it's necessary to complete such a international network of stations with some centralized office for collecting and publishing the observations from all over the globe and to work internationally together. It was clear very fast that progress is only possible if with international cooperation and since seismic waves, as I always say, are not stopping at national borders. His ideas were, after he died, taken over by many colleagues, and already in 1905, it was possible to invite to the first international seismological conference in Strasbourg. And this was a kick-off for international cooperation in seismology. The idea of a centralized office for all the observations of earthquakes is still very important. And today we have in England, in the UK, the International Seismological Center, which is collecting from seismic stations all over the globe the recordings and the readings. And what we see here is the distribution of seismic stations which contributed to the latest issue of the bulletin of the International Seismological Center, which was published now for the first half year of 2017. So these are stations which are from which are seismic readings collected. And the result of all these readings is for the same time period, the first half year of 2017, the observed seismicity, which we see here on this map now. And we see that most of the seismicity which is happening on the globe is somewhere in the oceans and remote areas, and many of these events were, of course, never felt by a person and were not destructive. Some of them were destructive. And so the old ideas of this are still valid and still producing results today. Although the idea that with seismic waves we can investigate the structure of the Earth came to quite well and well known and good results. The principal structure of the Earth, of an Earth, I don't know if you can see the mouse here, of an Earth mantle, an Earth core, and an inner core, this principal structure of the globe, of the Earth, was known since '96 when Inge Lehmann discovered the inner core and published a paper. I think it's still one of the papers with the shortest name ever, a paper just P prime. And with such a short title, she just invented and discovered and showed that it's correct that the Earth has an inner core and not only a core. And this principal structure of the Earth, crust, some lithosphere, stenosphere, mantle, outer core, inner core, was known since then, and the latest bit in the whole discoveries was then the big question: what is the state of the material in the different depths of the Earth? It was well known that the mantle is solid, the outer core is liquid, and not before about 50 years ago, in 1971, two seismological colleagues could show that the inner core is solid again. And this they showed with observations of eigenmodes of the Earth. After big earthquakes, the whole Earth is swinging like a bell. And these observations can be used to investigate the structure of the Earth. And these colleagues, Adam Juronsky and Freeman Gilbert, published in '71 a paper where they showed that these eigenmodes of the Earth can only be interpreted in the direction that the inner core must be solid. And since then, this is then the principal structure of the Earth is only known since 50 years. So this is one big part of seismology. And I have now here, without any preference in the listing, made 2 slides to show the principal research topics of seismology. Of course, one of the most important points is seismic source location, which is needed for all studies of seismic hazard, important to inform the public. It's important for geodynamics and monitoring of critical structures which are somewhere, and of course also important for the CTBT, the Comprehensive Testbed Treaty, to monitor the activities with respect to nuclear testing worldwide. And then we have a research topic, earthquake generation. What is behind the processes which are producing earthquakes, understanding these processes and conditions which are needed so that you get an earthquake. Seismic sources are a big topic, of course. The physics behind seismic waves, the excitation of seismic waves, the different types of seismic sources, from geotectonic to volcanic to cryogenic, atmospheric sources, hydroacoustic sources, anthropogenic, induced seismicity, explosions, and so on. Then the Earth structure and composition of the Earth is still, although the principal structure is known, in many ways unknown, and the deciphering of the unknown below our feet is still ongoing. I just make here as a general topic tomography. All tomographical methods had been very much also developed in context with seismology. Applied seismology is a big part, of course. Seismic prospection, searching for hydrocarbons or other energy sources in the crust or so. Active seismics. Then we have an environmental seismology, which is monitoring mostly, or concentrating on changes, monitoring changes of the near surface structures of the Earth with different methods and also different applications. Then the topic seismic hazard is of course very wide, and there we are working on microsonation, on the theoretical background of for the earthquake engineering community and similar questions. Seismotectonics, the stresses in the Earth and their geological effects are a wide used and topic. Historical seismology, of course, which is quite important because the instrumental seismology, our knowledge about seismology is about 100 years or a bit more than 100 years now. And what we all know is that the geological processes on the Earth have much longer time frames, much longer time periods. So we have to know what happened in the past with respect to earthquakes. And also the digitalization of historical material is there an interesting and important part. Seismic wave propagation is a very interesting and important part where we are working with theory and modeling of elastic waves and how they are traveling through the body of the Earth, eigenmodes of the Earth, body and surface waves, their propagation and modeling of these waves and comparing with observations. Observational seismology is somehow overlapping with many of the topics I already mentioned, concentrating on instrumentation, mostly networks, signal processing, analysis. I just want to mention that the smallest movements we are measuring of the ground, of movements of the ground, now is in the order of 0.1 nanometer. Now this is such a small amount of movement we can measure with our instrumentation and see the signals of seismic sources from far away. Then, of course, paleoseismology is also a point where they started the last decades, I would say, to dig in prehistorical or historical earthquake faults to see what really happened in the faults. And this is then hanging together, of course, again, with the seismic source processes and not only with seismic hazard and so on. So these are all research topics, and I may have forgotten the one or the other with which seismology is today dealing. And this is also somehow reflected in the objectives of the association I'm representing here, the International Association of Seismology and Physics of the Earth's Interior, which is a non-governmental, non-profit organization as your organization. And we have in the preamble of our bylaws these 4 points here. What are the needed, or what is the work we want to do in the association and promote? This is, of course, to facilitate research on theoretical, observational, and applied seismology, and the propagation of seismic waves, and discussing and design and adoption of methods and observatory praxis, and so on. And one important point is to promote the multidisciplinary research related to earthquake science and to for interpretation and inferring and interpreting the structure and properties and process of the earth. To initiate and coordinate the conduct and communicate of related research, which depends on cooperation between different countries. So still the old idea of international cooperation is still very important. And last but not least, which is also important and this year not so easy to do, is to organize and support international conferences and meetings focusing on the topics of seismology, and to support also, if the financial side is still supporting it, the participation in such meetings from people of young researchers or scientists from developing countries. So these are the objectives of our organization, and the IASPEI is not standing alone. We are one of the associations of the IUGG, the International Union of Geodesy and Geophysics, where the other geophysical and geodetical organizations are connected. And we have an association for the cryosphere. We have the International Association for Geodesy, for geomagnetic and aeronomy, then IAGA, then the International Association for Hydrological Sciences, then the International Meteorological Association and Atmospheric Sciences, then IAPSO, the International Association for the Physical Sciences of the Oceans, then IASPEI itself, and we, as an additional partner, we have the IAFSAI, the International Association for Volcanology and Chemistry in the US. And I just want to show here this slide with all, they have all these different commissions and all these structures, but I just wanted to show and that this inter-association activities, many of them have here some connection with seismology. And seismology is together with IAFSAI, the volcanologists, maybe the most interdisciplinary part of IUGG. And just to give some ideas where the overlap is with the other IUGG associations, with the cryosphere, we are working together for understanding and monitoring ice motions through ice quakes. Then the structure of ice sheets, glaciers, permafrost layers. There we have overlap with the cryosphere. With geodesy, of course, the figure of the Earth, the structure of the Earth, the general structure, observing lithosphere dynamics, plate tectonics. I just can give here some keywords. Rheology, GNNS, and so on. These are topics where we have overlap with the geodesies. Magnetic and space, Earth structure, again, the Earth geodynamo and the structure of the Earth core, there we are working together. Then, of course, seismology of other bodies in the solar system. Now is running a seismometer on the Mars and giving us information about the structure of our brother planet. And there were also seismometers running on the moon, and they gave important information about the structure of the moon. Hydrology, pore pressure is some information about pore pressure is important to understand source processes, because source processes are depending on the local structure where the earthquake's happening, and this is very an interesting part in this direction. Atmosphere, sound wave propagation in the atmosphere, infrasound, which is coupling in the ground. So we observe infrasound, for example, with seismic sensors, because the ground is moving, but also because the infrasound itself is coupling in seismic sensors, and they are interesting cooperations. The oceans, hydroacoustic wave propagation in the oceans, we call it T-phases. There are is a wave guide layer in the upper part of the oceans, which is used by the mammals to communicate over thousands of kilometers, but also earthquake signals are traveling there and other signals in the oceans. And of course, this gives information about the structure of the ocean, salinity, temperature are influencing this channel. And finally, volcanology, of course, monitoring volcanic activity by seismic methods is a big topic, and the structure of volcanic tomography again, and the terrestrial heat flow are their overlapping topics. But seismology has not only overlap with the other IUGG organizations, associations, but also with other sciences. I just want to mention here geography for global seismicity mapping, soil conditions, the physical geography gives information about the soil conditions in earthquake areas and how amplified seismic signals may become. Geology, tectonics, I have mentioned, dynamics and history of the Earth's crust are there the combining points. Geochemistry, Earth composition is of course then related to our investigations. Engineering, earthquake resistance in general of buildings, of structures. And of course, for the earthquake engineers, the seismic hazard investigations we are doing are basic for their risk analyses. Physics, wave propagation in general, high pressure physics, material physics, rheology. These are the topics where we have the biggest overlap directly with classical physics. Planetology, planetary structures, I mentioned, astronomy, helioseismology, the same methods which are used to analyze for the inner structure of the Earth of eigenmodes are used to investigate the inner structure of the Sun, for example. Signal processing is, of course, very important for us. Signal analysis, big data methods are now becoming more and more used. Near real-time data processing, fast computers, computing algorithms, and the result of this analysis to communicate with the public. Social sciences, mitigation of seismic risks, contributing to case scenarios, education and outreach. And finally, historical and archaeological sciences, discovery and interpretation of information in written sources from the past to have better earthquake catalogs. And archaeology is also in the last decades more and more we find investigations of archaeological destruction and with respect to interpreting them as results of historical earthquakes. So these are many of the interdisciplinary topics I wanted to mention here. To do this, IASPEI today is working in different commissions. We have a commission for education and outreach, for seismological observation and interpretation, for tectonophysics and crustal structure, for earthquake generation processes, physics, modeling and monitoring, for forecast. The whole problem of earthquake forecasting is not solved, and there are many ideas where people are working on. Earth structure and geodynamics. Then we have the Commission for Earthquake Hazard, Risk and Strong Motion, Strong Ground Motions. and earthquake source mechanics. I mentioned it before, and we are also working close together and with the International Heat Flow Commission, which is an inter-association commission. But as not many other associations or global associations and organizations, IASPEI has also regional commissions. And because it has shown that this cooperation cannot be organized on a global base, but we need also regional cooperation. And this started with the ESC, the European Seismological Commission, in 1951. And then in the 1990s, 1996, we got the ASC, the Asian Seismological Commission, and now relative new, the African and the Latin American and Caribbean Seismological Commissions in 2011 and 13. They are something like small IASPEIs on the regional base and try to promote the cooperation and to bring the science forward. So this, I think, and I try to give some overview, and I would like to finish this with an old slide from one of the oldest seismic stations in Göttingen, which was opened in 1903, or data from there we have since 1903. And there one of the founders of the theoretical seismology, Emil Wiechert, wrote, had as motto for the future of the work on seismology, a nice sentence, I think, which is here in German, originally in German, and I have here some translation to English. And the trembling rock bears tidings from afar, reads the signs, and this is something what we still do. We try to understand the motions of the earth. We record in all directions and to understand at the end each small movement. And with this, I would like to stop here and to thank you for your attention. And finally, I also would like to show this slide here, where you can note down and ask for further informations. Thank you.
Thank you very much, Johannes. And now I believe Daniela will also have a presentation for us.
Yes, Johannes must first stop sharing. I cannot share. Ah, yeah, no. Mm-hmm. So can you see my screen?
Yes.
Do you see the full screen now, or do you see this presenter view?
I see from the full screen only 1/4, also only.
Okay, let's try like this.
No. But it's larger now. It's just larger, but it's not. The whole thing is like zoomed in.
Yeah, it looks like it's cut a bit.
But you also only pressed the slideshow button, Johannes, didn't you?
Yes.
Okay, well, let me try.
Now it's
Now?
No, before it was better.
before it was, yeah.
Okay, wait. Once again. Like this?
Like that. Yeah.
It jumps then to another screen.
Why does it do it? But you also just pressed the slideshow button.
Mm-hmm.
And it worked very nicely.
It's sort
you
of.
See now only your screen?
Yeah.
Sorry?
You see only your screen now?
I see this presenter view of the
maybe you
slideshow.
should not go in the presenter view.
Yeah, but if I hide the presenter view, apparently it doesn't change much for you. Or maybe I am jumping too fast. Did it change for you now?
It still cuts it a bit.
No, everything is cutted.
Present, yeah.
Why?
I only see moment T und Netz.
Okay, that is very small. But we tested it before. Didn't it work there?
Yeah.
I think it was working.
When we tested it before, it was working, right?
Yes, it was.
Okay, and then I stop again and share again, maybe.
Yep.
Something with this. Otherwise, what I can also, as I share my entire screen, no, I can't.
Yeah.
What about now?
It's the same. It still cuts it.
That is really strange.
Yeah, maybe just show it in the PowerPoint mode.
Yeah, maybe.
Have the full screen.
Yeah. As soon as it allows me to go back, like this now. Now you can see that.
Maybe go back to sharing just that, just the PowerPoint window.
Okay.
Okay, yeah, like that.
So now you see it. Okay, then I stay in this view without going in the slide mode. Okay. So I will now present a more specific topic from seismology, which is the probabilistic moment tensor inversion for human-induced seismicity in the Groningen gas field in the Netherlands. And as you can see, it's a longer list of authors. So that was a cooperation between the 6 institutes listed below. And maybe since you are from the physics field and not from the geo field, you might be a little bit puzzled by some of these terms. So what do I mean by moment tensor inversion? Probabilistic, you probably never heard of the Groningen gas field and do not know much about earthquake source mechanisms. So in the following, I will try to build up these building blocks of the presentation and explain each step by itself. But I think you shouldn't worry if you don't catch all the details. I think it's sufficient if you manage to grasp the basic concepts behind these ideas. So first, what we record or what we deal with in seismologies are so-called seismograms, so records of earthquake waves that have propagated through the earth. And these already bear different signatures. One is that they bear also the signature of the receiver itself, the characteristics of that. Then they bear some signs of the medium they travel through, and they bear the characteristics of the source properties. And that's the part we want to explore further in the following. So first, for faulting itself, most natural faults or tectonic faults can be described by shear faults, and there are 3 basic types. One is here shown at the top. That is a strike-slip fault where the 2 blocks move in parallel to each other horizontally. Then we have normal faulting, where one block slides down with respect to the other, and reverse or thrust faulting, where one block slides up with respect to the other. In addition, some very special earthquakes may also have a volumetric change in addition to the shear faulting. And there are also, again, two basic types. One is compressional faulting, that is the example shown at the top. And the other is extensional faulting, which is shown at the bottom. But how do we get now from an earthquake to these seismograms? What happens? What do we record? So as example here, the earthquake is shown in the very middle of the sketch. And then we have such a strike-slip fault where the part which is closer to us now moves to the left, whereas the part behind moves to the right. And that means that there are two quadrants in this picture which experience some compression. So that's the two quadrants where the fault in a principle is moving towards two. And this would result, if we place a seismogram here at the side, result in a positive first motion. And in the other two quadrants, which are the quadrants the fault is in a way moving away from, if we place a seismometer there, we obtain a negative first onset. And now such source mechanisms are represented by so-called beach balls for seismologists. So I will explain how we get there. First, we look on the earthquake from below on the lower focal sphere, that is called. And the reason for this is historic, since, as Johannes explained before, the earthquakes were first recorded at teleseismic distances, so very far on the other side of the globe. So that would be the natural view to have then to the earthquake from below. And within the focal sphere, we now plot this fault plane we've seen below, above, and also the auxiliary plane. So we have these four quadrants again. And again, with the positive and negative first onsets. And that is now plotted in 2D as these beach balls. So it's just a view. You just compress the focal sphere into 2D and exchange blue and red with white and black. So that's the symbol which would be plotted on a map after an earthquake to explain to seismologists all over the world what has happened here. But of course, usually it's the other way around. We record the signal at the stations, and then we would like to know what kind of earthquake did we have. So there we come to the moment tensor inversion. So that's a backward process from what I explained before. So we would have these 5 stations here, which are plotted to the left. So for example, at station COL, we see that has a negative first onset. For station HON, that has a positive first onset. And now on this focal sphere, we place these polarities at the position where the station is located on the globe. So that's what you see here, the distribution. And now in the moment tensor inversion, we try to find the best fitting of these beach balls to explain the distribution of these polarities. And for this earthquake, that would be these fault and auxiliary plane. So that mechanism, but also instead of, that would be already fine to derive the mechanism for a shear fault. But instead of using just these first onset polarities, we can use the full amplitude that bears more information content. And instead of using just the amplitudes of the first onset, we can also use the amplitudes of the full waveforms or part of the waveforms that bears even more information. Mathematically speaking, the inversion process, why do we need it? So as said before, we record the seismograms on our receivers. That's here represented by the vector U. And these originate from a convolution of the source mechanism that is indicated here by the vector M. and by a matrix which contains the medium properties. That would be the big G here. But of course, we want to know now what the source characteristics are. So we want to get to the content of the vector M. So we have to make to invert the G matrix on the other side and multiply it with the seismograms. In our code, we went a step farther. So we are now doing a probabilistic moment tensor inversion. And basically, that means mathematically speaking, it's not an inversion anymore, although I will continue to call it this in the, for the next slides. But we changed this mathematical inversion by a forward modeling of a lot of potential solutions that is displayed here at the bottom. So first, the parameter space is sampled relatively uniformly, and then you try in an intelligent and effective way to find the best solutions within the full parameter space. That allows for using probabilistic methodologies, and that allows for estimating errors, which is usually not done in moment tensor inversion. So that's something rather new. So if you do an inversion, as shown before, in the mathematical sense, you are left with one single solution, but you have no idea how good that is. Oops, that was, yeah. So now we have the disadvantage of using not the slide view, since the animations will not work. So that slide looks now maybe a little bit puzzling, but I try to explain it in the same way as the animation would have built it up. So what you see here in the middle are the time traces, the seismograms we try to invert. In black, the observed, and in red, the synthetic one after trying to find a solution. And then between both these time traces, the difference is computed. That is here at the bottom. And this difference should be as small as possible to obtain the best solution, of course. Also here, we are not using this full long wave you've seen in the plot before, but we are using certain phases only. Therefore, we apply these taper windows, this gray box. And this here to the left, there's some information on the signal. So it has been recorded by the station G221 by the Netherlandic network. And it has been recorded on the vertical component. That's the meaning of the Z. The station has been at a distance from the event of 6.5 kilometers and an azimuth of -112 degrees. Then there's also a weight that results from the probabilistic formulation. So the seismograms of all stations are tried to be combined with different weighting in addition, and there's also the misfit. So that's the number we try to minimize during the inversion process. And our algorithm is quite flexible. So instead of inverting just these time traces, we can also invert for envelopes. We can invert absolute amplitudes, so just mirroring the negative parts of the time trace to their positive values. We can invert amplitude spectra, cross correlation traces, or amplitude ratios between certain seismic phases, so P and S, these are called. So quite a high flexibility of input data is allowed. And as I said before, the specialty here is that we do not get a single solution, but a whole group of them. So what's plotted on the left are inversion parameters as cross plots. And each of these small dots here represents one solution. The blue dots represent solutions which are not quite as good, and the more red this dot is, the better the solution has been. So each of those points symbolizes a different source mechanism occurring at a different location and a different time. And on the right, the same is plotted, but now in terms of earthquake location. So on the top left is a map view, and the other two are depth views. And these are just the best 1,000 solutions plotted here. And in total, we have tested almost 6.5 million models. From that, we can then derive the best mechanism, and we can also derive an average mechanism. And if the solution is stable, the best and the average solution should look very similar, which has been the case here. What's induced seismicity? What do I mean by this? There are some parts where inducing seismicity is intended. So induced means that the seismicity or the earthquake are generated by human interaction with the ground, by changing the stress field in the ground. So for example, the infamous fracking, or if we want to stimulate a geothermal reservoir, we have to build pathways for fluids, and that's done by inducing earthquakes. Very small ones, but still earthquakes. And then there are some areas where you unintentionally induce seismicity. For example, during fluid injections of wastewater and CO2, during mining. Here, for example, it's also a hazard, of course, for everybody who works within the mine. During oil and gas production, or also during building dams and tunnels. There have been quite some strong induced earthquakes. For example, in oil and gas production in the Wilmington oil field in the 1950s, there have been several earthquakes due to a dramatic subsidence up to 8.8 meters. In the Gasly gas field in Uzbekistan, there have been 2 earthquakes with magnitude 7, where it's at least supposed that they could have been induced. Usually for injections, magnitudes are lower, so between 5 and 6, but still large enough to cause damage. The largest earthquakes induced in mining were in Volkershausen and Newcastle, both with a magnitude of 5.5. And for example, if dams are built with water reservoir behind them, earthquakes may happen during impoundment of this dam, but also due to seasonal changes in the water level. And there have been several places on Earth where earthquakes with magnitudes larger than 6 have been induced in that cases. So, for example, Koina in India, Kariba in Zimbabwe, and Kremasta in Greece. But also weak induced earthquakes are something you do not necessarily want. Since these earthquakes, since they are caused by human interaction with the Earth, they happen at very shallow depths. That means that also small magnitude earthquakes may cause already some damage. They usually occur close to expensive equipment and may, for example, shear off bolts. They are scary to the population in the area, since they often occur in areas that are otherwise aseismic. And here are 3 costly examples. So, for example, in Basel in Switzerland, a geothermal exploration had to be stopped due to a magnitude 3.4 earthquake, with a lot of claims for compensation afterwards. In Blackpool, Great Britain, due to 2 earthquakes, the extraction of shale gas had to be stopped for almost a year. And Groningen in the Netherlands, which I will come to later, experienced a magnitude 3.6 earthquake, which also was followed up by 1,500 claims for compensation. As an example, here the US, and on the left, it's plotted with a black line that's going through here. The cumulative number of earthquakes over the years with magnitudes larger than 3. And as you can see, between 1970 and approximately maybe 1995 or 2000, there have been 21 earthquakes per year in that size. Between 2000 and 2005, the number already increased slightly to 31 events per year. And since then, it increased to 150 events with magnitudes larger than 3 per year in the US. And that's a number which is not, if it would be just natural earthquakes, this number would stay constant. But the increase means it has there's some new influence. And that indeed are human-induced earthquakes. And what is also, what was realized is that these happen not only there where earthquakes were happening before in the US, so for example in California, but all over the area. And they are caused, for example, by coal bed methane extraction, by oil and gas production, and by wastewater injection. So my example is a Groningen gas field, which is located here in the Netherlands. It's one of the largest gas fields in the world, and it's the largest onshore gas field in Europe. Within within the Netherlands, it's situated in the northeastern corner, and it has been in production since 1963. It's by now very well instrumented. So each of these small yellow and blue triangles marks one station. These stations consist of borehole seismometers, one located at 50-meter depth, one at 100, one at 150, and one at 200-meter depth, plus an instrument at the Earth's surface. And all this data is open, online, accessible for everybody. Seismicity first occurred in the early 90s. So there was in 1991 already a magnitude 2.4 event. Until December 2015, 900 events have been registered, of which 250 exceeded a magnitude of 1.5. And the largest event to date was the one I talked before, was with a magnitude 3.6. So on the left, you can see the distribution of these events over the Groningen field marked in red. They are quite, not quite regularly distributed, but over the whole area. And on the top right, there's a histogram of the magnitudes of the earthquake. You can see most of them have a magnitude around 1, but interesting is this tail here with magnitudes of 2 and also larger than 3. We tested a lot of inversion parameters and different setups, different input data and so on. I cannot show all of that here, so I will show only one example where we tested the inversion using different velocity profiles. So we arrive here, apart from we want to know what the source mechanism is, we now have to take into account the properties within the medium itself. And there we have two problems. So first, one has to know what the structure and the properties of the subsurface are in order to model the source mechanism. And there we are lucky, since here it's a gas field, so a lot of information on subsurface structure has been gathered over the years. Really quite excellent information. Still, we are left with a problem that we need to represent them in a model. So even if you build a full 3D model, it will never represent the full truth. It will always be just an approximation. And for our algorithm, we needed to reduce from 3D to a 1D model in addition. So these are the 3 velocity models we tested. So that's velocity, seismic velocity of a certain wave phase, and in kilometer per second on the x-axis, and on the y-axis we have the depth. So in blue, we tested the NN model, which is the model used by the Seismological Survey of the Netherlands for earthquake location. We tested the KD model here in green, which is already a bit more complex. That was used by a previous publication for earthquake source mechanism inversion for this field. And we built the N3D model here in red, which is an average from a group of 1D velocity models extracted from the full 3D velocity model. And as you can see, it's the most complex one, containing also these 2 very high velocity interfaces. When we have a look at the results, we can see that for both the NN model on the left and the N3D model on the right, the waveforms can be fitted quite well. But the mechanism that results is very different. Also, if we look at other plots of results, so here on the top in terms of earthquake locations, and at the bottom in terms of earthquake mechanisms, we see that for the N3D model, the variation is smallest. So, and in this case, less variation is good and induced indicates stability of the solution. In addition, we now included also the volumetric component in our inversion. So not only trying for a shear fault. And again, these plots, they illustrate the different mechanisms we obtain. they are quite distributed in this case, since also the mechanisms change very much. It indicates unreliability of the solution. So our preferred solution is the one we obtain with our own 1D model. And what does this solution now mean? Actually, this small beach ball here on the top right, that can be separated into one part which indicates normal faulting, so one block sliding down with respect to the other, and a collapse at reservoir level. And that makes a lot of sense for an earthquake happening in a gas field where gas has been extracted since decades. So my take-home messages for you are that geological structures, as for example faults, as well as their root causes, which would be earthquake sources, can be described by mathematical concepts, such as moment tensors. A full moment tensor describes shear faulting, but also includes a potential volumetric part of the source. Earthquake wave records, so-called seismograms, contain information on earthquake source mechanisms, but also on the properties of the medium through which they propagated. During most of the existence of planet Earth, earthquakes had natural causes, but within the last century, human undertakings also sufficiently influenced the stress field within the Earth to cause earthquakes, same as with climate change in a way. And such earthquakes may be quite scary for the population and need to be analyzed in the hope that they may be avoided. In contrast to natural earthquakes, which usually can be described by shear faulting only, such induced earthquakes often contain also volumetric components. And the probabilistic inversion method presented here has the advantage that we obtain a group of solutions allowing for an estimate of uncertainties in addition. So I hope that you are no longer as puzzled as at the beginning and understood some of, at least of these concepts. If you are interested in further information, just write to me. And thank you very much for your attention.
Thank you very much, Daniela. And thank you both again for your very interesting presentations. I want to just apologize for the background noise that I have, which unfortunately I can't avoid at the moment, as this is the only place that I can get a stable internet connection. But I think we can move to the Q&A now. And I already have a few questions here for you from your presentations. And maybe we can start precisely with your presentation, Daniela. And if you could maybe elaborate a bit on induced seismicity and how for the knowledge that we have of what of the processes that cause induced seismicity, what can we do to avoid that, and maybe if you or Johannes could maybe also have some input on this. Does IASPEI in any way try to, for example, counsel decision makers, both in terms of companies or governments, to maybe try to avoid the processes that cause induced seismicity?
Maybe I start and then I give over to Johannes for the IASPEI part of the question. Well, it's a $1 million question, how to stop induced seismicity. In a lot of cases, this means stopping the actual operation, as for example has happened in Switzerland and Basel, or also at Groningen now. So the amount of gas that has been extracted from the field was continually reduced in the hope that seismicity would stop, but it doesn't. Still, there are happening earthquakes and also some with larger magnitudes. So the Netherlands actually will stop producing from this gas field, although quite a lot of gas is still in there. That said, For geothermal explorations, for example, some colleagues from the GFZ, the group of Marco Bonhoff, they work on developing strategies for how to inject the fluid which is necessary to make the new pathways in a way that not or only small earthquakes are generated and no longer some with larger magnitudes. And with a test experiment in Finland, it looks as if they had quite some success in that. But this will not be possible for all operations. Yeah, so then maybe Johannes can answer how the IASPEI is dealing or if they are counseling for induced seismicity.
We have to be aware that whenever we are changing somehow the crust, we are inducing some changes in some stresses and some load, either by hydrostatic load or whatever. If we take something out, we are making some holes or some voids, and either the material around is good enough to keep the void and nothing happens, or the stresses and the material around are so that you get a collapse, for example. Whatever you do, you will get some effects. And one cannot say that, it's not so that IASPEI has some principle decision or some principle politics or so. The point is only that we ask that if people are starting with some activity, that they contact the scientists, what they can maybe expect in this area, what they can do. That we also ask for the researchers to continue research to better understand and to better get an idea what you can expect in this and this area if you make this and this changes. And then, of course, then the decisions are then made by politics. It's not so that IASPEI can say you should not do this or you should not do this. We can only say, and this is, I think, also the right way for science, that we ask for objective and analysis of the situation and of the consequences and what the different scenarios may contain. And then the decisions have to be made by others. Yeah, so.
Very well. Thank you very much. As a question, maybe now more in general, not necessarily induced seismicity, but regarding like seismicity in general, what kind of, let's say, predictory power can we have, you know, regarding the knowledge that we have obtained from accumulated stress on the several geological structures that have been studied so far? What kind of predictory power do we currently have? Is this, can we sort of say that within a matter of years something will happen? Within a matter of months? What is the time scale for which we can currently reasonably predict something, some kind of energy release to happen, so that we can, for example, as you were saying, IASPEI itself engages a bit in education and outreach. So what predictory power do we have to try to adapt to situations, warn people with some time, and prevent any big damage from occurring.
Yeah, seismology is far away from what one expecting from weather forecast. The problem is that we are observing changes of the stress field and of the conditions under which the material is at the surface. And we want to predict something what is happening in 10, 20, 30, 40 kilometer depths, where we have no sensors. The deepest hole which was ever drilled in the crust was going to 11 or 12 kilometer at one point, where they had the chance to come so deep. And so we have absolutely no knowledge about detailed of stress field measurements online, also down in the crust. On the other side, we have, of course, we know something about geological processes. We know about mean movements over millions of years. So we know the history at many places also not, of observed earthquakes, so that we see maybe some pattern. The movements are so much that this accumulates. On the surface, we have, of course, GPS, where we know now much more about relative movements of different structural components, but these are all movements what we are measuring, which partly are compensated by not by earthquakes, but by deformation. And how much the rate is between how much this is compensated by earthquakes or by deformation is unknown. So there are many, many unknowns. So what we are doing as seismologists are working with statistics, trying to make a statistic and to say, here we have this and this history, and based on this statistic and on this general behavior, we can expect this and this earthquake scenarios in this area. So then we give some probability that a magnitude 5 or 6 event may happen here within the next 50, 100, 2000 years or whatever. But of course, this is probabilistic research on with very small numbers. So you have also in your observations, you have uncertainties. So all this is not solved, and what has been done during the last, I would say, decades is to push much more in the direction that instead of looking to forecast an earthquake, which means you need time, magnitude, and location, otherwise it does not make any sense. Instead of going in this direction, to go in the direction that you have a better preparedness, that you go in the direction of supporting better building codes, to say, in this area, in principle, you have this and these problems, please build so and so that if there comes an earthquake, if it comes this year or in 200 years, nobody knows, but one has to be aware and to be prepared. And with this, I think we really made also globally some big progress. if one looks the regular earthquakes, magnitude earthquakes of 5 or 6, which are happening in Japan, they are almost not having big effects. Some have, but many of them not. And if you compare this with some other countries where the preparedness is on a totally different level, where it happens that magnitude 4 earthquakes are killing people, this has and have not to be. Yeah. So I think the direct forecast one can forget. The general tendencies, the general scenarios, what maybe happen, there one can do something, and most important is to be prepared.
And also maybe what we can add is that also during the last decades, but that's still a hot research topic, is the earthquake early warning. So that you have instruments in areas where you know that are very earthquake prone. So these instruments will record the first large waves arriving, and then your signal transmission is faster than the earthquake wave travels at the surface. So you have some seconds up to some minutes of warning, for example, for industrial operations where you can shut off valves and so on, or your nuclear reactor, turn it down, or warn in larger cities so that people know there's an earthquake coming, so they can cover. And along with rapid response after earthquakes, so that you build up systems where the first responders can see very quickly what has happened or what was likely, which area is likely to be very destroyed, who needs the most help.
Yeah. But of course, this includes that you will always have some blind zone in where the earthquake itself happens. But yeah. And earthquake waves are fast. This one should really keep in mind. Yeah, we have velocities of kilometer per seconds. This is quite fast.
Yeah. Yes, definitely. So I have another question. Essentially, how does, for example, Johannes mentioned that there's also the study of helioseismicity, for example. So how does the study of seismology in other bodies within our solar system, for example, is there also a component of the study of these of seismology in other planets within our solar system, in other planets outside of the solar system, for example? How is the study of seismology in other celestial bodies help us with the study of seismology in Earth itself?
No, I don't think that we can learn about the Earth by measuring seismic waves on the Mars. We know much more about the Earth than about the Mars. This is cooperation and with planetologists to know more about the Mars. And the same is true for the Moon. It's of course, you may measure some unknown phenomena and then starting to try to interpret them. But this all is based on what we experience and measured and our knowledge here from the Earth. And as I said, yeah, there were 2, 3 or so, I think, seismometers with these Apollo missions on the Moon. And there is now one seismometer on the Mars. And the data volume is quite limited with respect to what we have from the Earth. And of course, we learned from the Earth how to interpret seismograms. If you have a long series of different wiggles and after an earthquake or after an event somewhere, and how to interpret them, how to look in them, the different types of wave, separating them and so on. And with this one can directly, even from one station, one can start to locate the event. Where was it? And the same methods one can then, of course, apply to even if one has only one seismometer on the Mars. So it will tell us, hopefully, more about the Mars.
Thank you very much, Daniela. Any thoughts?
No, just adding maybe that in addition to placing seismometers on Moon and Mars, there are also seismologists working on helioseismology, so observing waves on the Sun, but obviously not by placing an instrument there, but by using photographs. But that's an area I don't know much about, actually.
As I mentioned, yeah, you can see patterns of the surface if you see the surface of the Sun moving, and there you see patterns, and you can use them to interpret like eigenmodes if the Sun is pumping up and down, and to investigate then the structure of the Sun. And I think helioseismology has also been used even for other stars and not only for the Sun. But of course, the resolution is there because much lower.
Thank you very much. There's just another question on the field itself. So how much something like field work can be expected? Have you so far in your studies of seismology, have you yourselves engaged in field work? Is it usual for scientists that research in seismology?
You want to start, Daniela?
Well, it depends a lot on in which area you work, actually. So yeah, it depends on which topic you are researching. It depends on the institute where you are working, or if you are even working, for example, in industry outside. It depends a lot on your job. So, but that said, it has, I guess, the amount of fieldwork has declined over the last decades as the use of computers went up. That would be my impression. But it's still possible. So I still also participated in fieldwork, and actually I like it a lot to be outside of the office and do some practical work. And Johannes has some more exciting experience, I guess. You can say something about the Troll station.
Yeah, fieldwork is of course a lot involved if you are planning and building somewhere new stations. And I was involved in building new seismic stations in the European Arctic and in the Antarctic. And so I had the chance to come to Antarctica to build the a seismic station and install the seismometers in 2012. And the data are still coming in via satellite link and can be used. And similar things in the European Arctic. So this is part of, if you are working in seismic networks, you have to go to the stations, which are often at remote places. In particular, since you are interested in small signals, it's important you go to places which are not in the center of the city, where you have a lot of noise produced by each car driving and passing by. But you want to go somewhere else where hopefully nobody is going, so that you can measure these small signals of below 1 nanometer. And so there is some trade-off between the seismic station installation and remote and quality of seismic stations and how far and how remote they are. Another point is, of course, as Daniela mentioned, the industry, the decades of search for hydrocarbonates all over the globe was involved with a lot of field work, and this seismic prospecting along lines, either with ships somewhere and or somewhere on land. It's where a lot of traveling for seismologists and field work. Also, field work is definitely paleoseismology, where you have to dig out and so on. So there are many possibilities, but as Daniela mentioned, it's very much depending on which part of seismology one is concentrating and doing the work.
Okay, thank you very much. So I now to take this on a more general note, but also in a way specific, I just wanted to ask both of you how you sort of decided or how you got involved with this field of seismology, and what advice would you give to any students considering the field? So what they should explore, what organizations maybe they can follow to have some, to be able to follow the most current research. So something along those lines. Maybe Daniela can start.
Well, so I studied geophysics in Münster and then went on to a PhD in Hamburg that both had nothing to do with seismology. That first came when I did an internship at NORSAR. So there I directly started with a moment tensor inversion before going back for a postdoc to University of Hamburg and working on a different seismological field before turning back to NORSAR. So for me, this internship got it started. And that, I think, in general would be, that does not only apply to seismologists or geophysicists, but to a lot of students, I would always advise to do internships. And if you have the chance also to do it at different places and different kinds of places, maybe at a research institute, but maybe also one in industry, so that you can see for yourself where your interests are really lying. I think that's difficult to conclude from just listening to lectures. Yes, what institutes to follow depends probably a bit on where on the globe you are. So I think there are a lot of interesting geophysics and seismologist research institutes like ETH maybe, or SED in Switzerland, the GFZ in Potsdam, NORSA in Norway, and I don't know, Stanford also in US. So I would start out with your region of the globe and search in your country what you can find. And maybe IASPEI has a nice webpage.
I don't know so if our webpage is so good, but no, I was just thinking, how was I ending in seismology? After I left school, it was clear that I wanted to do something with physics, but I wanted not to make. I was on the other side also very interested in all what we had to do with our globe and what's called geo, and therefore I was looking for geophysics, and the institute where I started, Frankfurt, was very much seismology oriented. The part of seismology as part of geophysics. And so it was somehow then just straightforward to land in seismology and not in another direction of geophysics. What I really think is that to go for geophysics and seismology, it's very good to have a good basic education in physics and mathematics. And if you have this, you have a chance also not only to be or to become a good seismologist, but in general, a good geophysicist who can be able to go in different directions and so some things are chances, some other things, yeah, you may have started with geomagnetic and found out that you don't get a job, but if you have the right basic education, it's no problem then to change to seismology, yeah, and if you have learned enough, and so there is a lot of flexibility, and at the end one should do where you are mostly interested in, and there you will also then develop your own interest most and being most engaged in the whole topic, and not going one direction just by thinking, oh yeah, there I may make maybe more money or whatever. Then you will not becoming there a good researcher in this direction. But,
maybe some encouraging words would be that usually people coming from physics to geophysics have a very sound understanding in physics already. That's very good. And also are not afraid of equations and integrals and so on. So physics is a good base to continue into geophysics.
Yeah.
Okay, thank you.
The basic of seismology is a wave propagation of seismic waves, is elastic waves, is physics.
Okay, so just as we don't seem to have any more questions, maybe I would just ask you if there's any way for physics students interested in the field to either get involved with IASPEI or maybe just follow the work of the organization?
I think this is mostly depending on the institute where you are getting your education. If you are in your institute interested and working together with some professors on this topic or helping in this topic, then you will learn somewhen that there is this and this conference, there is this and this meeting where results are presented, and one has to start or can start early to go on conferences and maybe you are sitting there half the time and don't understand anything, but something is sinking in by time. And also this is very important for, especially for seismology, for building up your international network of colleagues and to get connections worldwide. So I would say this is would be the natural way to go, to be open for participating in workshops, in conferences, and then one is coming in the system. There is I get often the question how I can get member of IASPEI. There is no membership of IASPEI. Yeah? There is no member. We assume everybody who is participating in some conference of IASPEI as member, and that's it. And if somebody shows interest, they can get the newsletter where we distribute some general information. Most important for many is maybe the list of conferences we are having there, and where one can plan to go. And seismology, okay, this is this year not really so easy with conferences and workshops, but I have seen quite a lot of the globe by just participating in conferences and going there, giving a talk, hanging a poster, meeting people, and yeah, making friends.
Of course, that is precisely, that's also something that we, IAPS also aims to provide to the students of our community, that sense of the importance of networking, of meeting people from around the world, people from different universities. So it was quite sad that we weren't able to have our major conference this year, but hopefully next year we can resume those activities. And in the meantime, we're having these very interesting sessions. And in that sense, I would now ask you if you have any final statement, any final message that you would wish to leave to any student watching this right now or that watches this later. Maybe
yeah,
if Johannes wants to.
Okay, I think that or let me say, I hope to make or made seismology a little bit interesting for students of physics, to be maybe just yeah, to get the idea maybe to go in such a direction. And when one is finishing or when one has to decide which type of physics one is continuing, and that there are possibilities which are maybe not so openly known, but that seismology is a very wide field and opens really for interdisciplinary and international cooperation and work together. And who is interested in such things, we are happy about every good person coming in.
Very well. Thank you very much, Johannes. Daniela?
Yeah, maybe like Johannes said before, search for a type of work you really enjoy so that you can really engage in it. Then work together with your colleagues, do not work against each other. And if you have questions, just ask, and also be not afraid to just send an email to someone more senior, someone somewhere on the globe.
Yeah.
Very well. I want to thank both of you again for your availability to participate in this session. I think you gave a good overview of seismology, and we as students can with this sort of understand that it is a wide field. There's a lot of opportunities in this field, and hopefully physics students consider it throughout their studies, because of course all fields need their researchers, so you should always try to consider as many fields as possible before starting actually narrowing down your choices. So thank you very much, and thank you also to everyone watching us and everyone that watches this later. We will continue throughout the next days and next week as well with these series of sessions of IAPS at a distance. So everyone have a very nice day. Goodbye.
Thank you. Okay, goodbye.
Goodbye.